So suppose that we are going to start with say n equal to say 1000, right? And let me take the lambda value equal to 0.03, right? So see for the time. So first column for time, this is for n of t, and I generate for e of t, right? Okay. And say start from the 0. So this value was equal to j $2. So I have picked the value from that particular column, right? And this value is equal to whatsoever value I get here, whatsoever value there, it should be subtracted from 1000, right? So that is to automate the sum of the calculations. So for example, I take a step of 2, right? And I know that this is equal to n naught e to the power minus lambda t, right? That's fine. So n naught value, let me take j. Okay, this can be taken from here, and I would keep it fixed. So let me take it b $2. So the value from here times the exponential function is available from here. So see the other markers below it, exponential dot distribution, right? So IM exp. Well, we have to check it, right? Exponential e to the power minus lambda value. So let me get the value from its position, j3 times the t value. The t value is equal to, and that's it. So 941 and 58, right? So in similar fashion, if I look for further time steps, okay, and if I repeat the calculations, so this is going to be the process, right? So n is going to decrease, right, with time, and daughter nuclides would increase, right? And in similar case to the looking for the lifetime of the bulbs. So if you start with the 1000 bulbs, so some would fail in the first few hours, then the rest would fail, they will continue, right? So you can get an average value. Now, let me define a quantity which is like probability. So probability, of course, I can require two values. So number of nuclides that have decayed. So these are very much the daughter nuclide quantity, right? Number at this value, number at the previous time, right? And divided by the total exposed to that experiment. These are this number, right? Right. So very much expression like n naught minus n divided by n naught, right? And then, yes, I could taken that 1000. These are daughter nuclides, right? At this level, number of nuclides that has gone to decayed state, right, during the 2, right? So if you like, you can write it. Okay, let me write it in this fashion. It should be B3, okay, B2 minus B3 divided by B3 Okay, that's fine. Divided by B2 and then multiply by divided by the delta t time, which is equal to, in our case, it is equal to 2, right? So it is this number. And if I continue this calculation, so see for these numbers, right? So the number, wow. The number is, okay, let's check the calculation. So numbers are updated, but the number is almost equal to 0.03, right? The number is almost equal to 0.03. Let me change this number here to 100. Okay, so still there is no difference, right? So it is 0.03, the lambda value, right? So that is the decay probability. This is the decay constant, right? Okay. Now, in order to generate the functions, so so let's define some normalized functions. So I define the reliability function. So this is the normalization of n, right? So I define with all values of n divided by j dollar 2, which is the initial value of n. So it starts with the value 1. It starts with the value 1, and then it moves on, right? So that is going to be the case. And for failure function, of course, it will come from the daughter nucleide here. So that will be the okay. Well, there is some problem with we didn't correct that one. When we change the value of n from 1000 to 100, we didn't change the value of n. It is still 1000 minus B2. It should be 100 minus B2, right? So for 100 nuclides, it should go like this, right? Okay, so that's logical. Now f of t, right? So similarly, it is this one, right? It is like daughter nuclide, so it should be equal to this value divided by j dollar 2, right? So it starts from 0. In probability terms, it goes up to the highest value, and finally it will saturate at 1. Now let me define a function which is similar to activity function, right? However, it should be normalized. We know that the activity expression, right? So divided by naught, right? So I define this value numerically, and this is equal to here function. This will be equal to the value at the next step minus value at the previous step and divided by time, dn by dt, right? And divided by n naught, right? So when I am going to compute it from f of t, there is no need to divide it by n naught, right? So divided by 2. So that is going to give us a value okay. The value starts with 0.002, 0.0029. So it is close to 0.03 value, right? the lambda value. That is the case of exponential distribution where the lambda value stays constant, right? This is this is known as f of t, is a derivative of that one. This is known as the failure density function. Failure density function. And the lambda is also known as r of t, failure rate function, that we have already computed in the column of probability. So this is known as the lambda function or function r of t. This is known as r of t function in reliability, right? For reliability, we define these four characteristic function, right? One is the probability, right, which is r of t, and it is analogous to lambda, which is the number of decay probability per unit time. We have r of t function, which is the reliability function, which is similar to the behavior of n of t, a normalized one. We have the f of t function, which is similar to the behavior of daughter nuclide characteristic, and then f of t, which is analogous to activity of a radionuclide. These four functions are known as reliability